Hi, I'm Dustin. Really great to be here. Quick things about me. So I'm a developer advocate at Google. That means I represent the Python community when we build things internally at Google Cloud. I'm also the chair for PiType. So I'm from Austin, Texas. If you want to come visit Austin, I know a lot of people are interested. We're going to be May 16th and 17th next year, coming to PiType. I also work on some Python things, including the Python package index. But this talk is not about that. We're going to talk about static typing. And I want to start with pop quiz. So pop quiz. Is Python dynamically or statically typed? Who thinks it's dynamically typed? Who thinks that this is a talk about static typing in Python? It's probably statically typed. Anybody? No? Who thinks this is a trick question? Yeah. All right. It's a trick question. So the answer is that Python is dynamically typed, but it can optionally be as statically typed as you want it to be. And if that doesn't make any sense to you, that's okay. You're in the right talk. And we're going to break down everything necessary to really understand that answer. So to understand that, we need to understand about types in Python, type systems in general. We'll talk about dynamic typing in Python. Then we'll talk about static typing in Python. And once we understand that, we'll also talk about how to use static typing in Python, when you should use it, maybe when you shouldn't use it as well. So let's talk about types, and specifically let's talk about type. Let's talk about the built-in type keyword in Python. So in Python, in our REPL, we could type something like this, type of 42, and we get something back that says it's class int. So 42 is an integer, that makes sense. And we can do the same thing for floats, strings, lists, right? The type built-in tells us what a variable or what an object is. So you might say, oh, like I recognize these things, string, int, float. Like this is what I use to change one type into another. So yeah, you could have a variable like this, set a equals to 42, you get 42. You can call float and you get a float. You can call string, you get a string. You can call list and you get a really ugly list. Who's seen a really ugly list like this before, right? Where a string is getting turned to list. That's a type error. You've had a type error in your code where something that was expecting a iterable or a list got a string instead, and Python did this. All right, so yeah, you're still in the right place. And the thing to note here is that, like, yeah, these are kind of look like the types that are available to us, but they're actually just classes that correspond to built-in. So like, int is actually just kind of a alias for a class in Python. So when I call type of 42, I can compare it to int. It's just doing class matching, right? I can say is instance 42 of int, and it will tell me if it is a part of that class or not. But there are other types as well, right? Maybe you've gotten like a none type error. None type is the type of none, but we don't see none type as a keyword in Python. We just see it in our stack traces. Similarly, there's a function type, but we don't use the word function to define a function in Python. We say def, function name, open, close, paren, et cetera. There's also like an ellipsis type, and actually there's a lot, right? So in Python, if you import types and you call dir on types, you get this whole list of all the things that exist in Python that could have a type. So there's like a code type, you see function type is in there, there's all sorts of types. So you could like instantiate a function with these classes. It's just a class, they take arguments. We don't because it'd be really messy, but yeah, these types are available. So when we say that Python is a dynamically typed language, what does it mean? So basically it means that, first of all, a variable can be any type, right? If I assign something to be a variable, it can contain any of these types that are available to us. So for example, I could import random and set the variable a to be the random choice of an integer, a float, and a string. So what is the type of a here when I evaluate this? Well, it depends, it's non-deterministic, right? It depends on which random object was chosen from that list. So it could be a string, could be int, could be float. It doesn't matter. That variable can contain any of those types. Dynamic typing also means that the arguments and return values from a function can also be any type at all, right? So the same is true for a variable as it is for a function's arguments as it is for the return value from a function. So if I had this function like this, frobnicate takes 3 arguments and returns a plus b plus c. So when we write a function like this, how do we know what types this is going to expect? Like, does anyone have a guess what a, b, and c should be here? Like, okay, maybe they could be integers, right? So yeah, if I define the frobnicate function and I call it with 1, 2, and 3, it correctly adds them all up to 6. But I could also call this function with strings. and it would concatenate the strings instead. This function can accept any of these types as arguments, and it would still work, right? It's still a valid Python function. The thing I can't do is mix these types, right? I can't add integers and strings just with the plus operator. So this would create a type error, right? I'm trying to do something and the types are incompatible. All right, so that's confusing. This function is confusing. How could we fix it? So one thing we could do is we could write really long and detailed doc strings that outline every single type that the function expects, what they are, and what it returns. Who writes doc strings like this? Anybody? Okay, for those of you with their hands up, is your employer paying you enough to write doc strings like this? Because it's a lot of work, right? Okay, maybe, yeah, that's good, good. Talk to those people later for jobs. Yeah, this is good, right? It's a lot of documentation, but it's also a lot of work. And while this is great to read, the thing about this is writing this doc string has zero effect on whether this function is actually being called correctly or not, right? You're telling the developer that's eventually going to come and try to use this is what I expect, but there's no guarantee that they're actually going to do that. They might still be calling it with strings or mix of strings and integers. Another thing we could do, we could assert on the type of everything that's passed to this argument, do our business logic, and then assert on the return type before we actually return it. So I gave this talk once before, and I was like, nobody does this. This is insane. Because the thing is, this actually adds overhead to the execution of this function, right? There's a small cost you have to pay to do all these assertions, unless you optimize it out, which maybe you're not doing, or maybe you are doing. I gave this talk once before, and someone said, yeah, actually, we do this. And then the thing is, it works, right? It's a valid way to assert on the types for your function, but it's so many lines, right? And what if you forgot an assertion, right? It's on you to remember that. So what do we do instead? In Python, what we do is called duck typing, which means that if it walks like a duck and quacks like a duck, it is probably a duck. So basically, based on how we use a variable in line with function in Python, determines actually what we might interpret it as its type to be. So for example, in this first line here, I'm setting foo to be f of x for x in bar. So we could probably reasonably assume that bar is an iterable. Like maybe it's a string, maybe it is a list or something similar, a set. The second line, we're comparing bar to 0. So bar is probably like a number, maybe an integer or float. It's unclear, but we have a pretty good idea what it is. And the last one, again, like that could be a function. It could be a class that's poorly named, it doesn't start with a capital letter, but we don't know, right? It could be really anything at this point. So, static typing. There are actually lots of statically typed languages. And static typing is basically the opposite of dynamic. It means that the type of a variable, the arguments to a function, and the return type of a function are statically defined and they cannot change. They have to be a specific thing. So here's some examples of that same Frobnikite function in other statically typed languages. And I'm curious if people can recognize these languages. So here's the first example. Anyone know what this is? I heard it. Yeah, that's C. How about this one? Java. It's like a dead giveaway with a public static int, whatever. Anyone know this one? I think I heard it, yeah. This is Rust. Rust has really fine-grained integer types. This is an unsigned 8-bit integer. How about this one? The number is the hint here. So this is TypeScript, which is type JavaScript. In JavaScript, there's only one number type. Everything's a number. So that's how you would know. All right, so you can sort of put languages in these two categories, right? There are dynamically typed languages and statically typed languages. And I have to put a little asterisk here next to Python, which is why we're giving this talk, is because Python is, and it was originally, a dynamically typed language, but it is now kind of also statically typed. And also, technically, Ruby is going to get a similar type system to Python, but not till the end of next year, so I won't include it. So, like I said before, Python is a dynamically typed language, but it can optionally be as statically typed as you want it to be. This wasn't always true. When Python was first created, it was purely a dynamically typed language. And the story of Python becoming a language that is optionally statically typed is also kind of the story of type checking at Dropbox. So Dropbox is a large software company. Some people might be in the audience here from Dropbox. They have millions of lines of Python code. And basically at that scale, having that many lines of untyped code is a liability, right? It becomes exponentially harder for your developers to interpret what this code does when they inherit new code bases, when they are doing refactorings and that kind of thing. So pretty early on in their journey through having that much Python code, they determined that, oh, it's not great that Python is dynamically typed in this case because it makes it hard for us to work with it. So it's largely a story of static typing at Dropbox, but there were some other things leading up to it as well. So the first is PEP 3107. So we got this in Python 3 in 2006. And this allowed us to do something called function annotations. And what this meant is that I could take a function like this, and I could add any metadata that I wanted to the arguments and the return type of this function. So anything that's valid Python could be put in after the colon here. And what I would get is if I define that function and called under annotations, got that attribute off of it, would be the evaluation of all those annotations in a dict and the return type and all those things, or the return annotation. So here I'm just, these are just made up things. It doesn't really have a lot of meaning. And that was the thing, like it was basically a nice thing, and there were a lot of things that could be done with it. All of them kind of boil down to maybe we can do type information with this. And so there are a lot of different ways that maybe we could do that, do it with databases. Could also just use it as documentation, but really this was like looking forwards to having type annotations for functions. So this allows us to actually write a function like this, which is kind of actually interesting. So here you can say the type for each argument and the return type, and then you have annotations that would tell you what the developer was expecting when they wrote that code. But it still doesn't give us a way to actually evaluate whether that function is being used correctly, right? It just gives us annotations and now an attribute that tells us what those annotations were. And this is just for functions. You can't do variables here at all. So around the same time, Yuka Lekpaslo was working on his PhD thesis at the University of Cambridge, and his research was about the unification of a statically typed and dynamically typed language. And his goal was to be able to use the same language for everything from a really tiny script to a sprawling multi-line code base and add as much typing as you want. He wanted to have this gradual growth from something that was completely untyped and allow you to slowly mix in and add static typing to it. Sounds kind of interesting. It'd be great to not have to do it all at once, especially if you have millions of lines. So in 2011, he published his PhD thesis, and basically his conclusion was this. If you try to add a static type system to a dynamically typed language, it could be totally invasive, right? You'd have to change every tool in the ecosystem, every interpreter, everything that checks syntax, et cetera. So this was his conclusion. However, he found that if you created an optional pluggable type system that doesn't actually affect the runtime of the program, this could be added to everything without causing significant burden to the ecosystem. And so this sounds really great. And what he did was he took his PhD work and he went to PyCon US in 2013 and he introduced something called MyPI. So if you've heard of MyPI before, what he introduced was not what you've heard of before. In the abstract for this talk, he describes MyPI as an experimental variant of Python that supports writing programs that seamlessly mix dynamic and static typing. So this wasn't a type checker, although it included a type checker. It was actually a variant of Python. In his research, he couldn't use Python to do his research, so he created a new language that kind of looked like Python that allowed him to actually do research about the type systems. So MyPI, the language, looked like this, and it kind of looks like Python, but you see that it has int fib, that's defining the type of that function, and et cetera. So the issue is that Python at the time, even with function annotations, it wasn't enough for him to actually use Python to do static typing research. But he presented his project at PyCon, and he said afterwards he chatted to Guido about it, and Guido convinced him, yeah, let's get rid of this variant of Python. Let's try to just do this in pure Python. It would make a lot more sense, and we would get some benefit from it as well. And so the variant went away, and MyPI became just the type checker that was included with it, and that is actually what we think of, and what we'll see becomes MyPI today. So shortly after that, Guido published PEP 483, which is his theory of type hints, basically the idea of how types and static typing should work in Python. And so this is some really broad and general ideas about just typing in Python in general. So the first tenet of this was that typing should be optional. And you can sort of see that this is sort of coming from Yuka's research. Basically, adding an annotation to Python code shouldn't affect the runtime. It should have zero effect on the actual runtime of your program. That means that an annotated function should behave exactly the same as one that doesn't have any type annotations. And I think this is kind of some lessons that we learned from the migration from Python 2 to 3, right? We want this to be an easy transition from untyped to typed code. And we also want to be able to do it piecemeal, right? Like Luca presented in his paper, we wanted to do gradual typing. You want to be able to add typing to certain files in your code base and not have to do it all at once. In addition, we should have variable annotations. So just functions is not enough. We need to be able to tell us what the types of certain variables are in Python. So that means that we could do something like this, where while we have the function annotated, we should be able to say something like, the type of this variable that I'm assigning to is an integer, and then I can return that. And this also means that we can do type hinting for Python 2. So as long as we have this sort of like comment notation for variables, even those that have old versions of Python should be able to use static typing. So this allowed us to do all the same types of annotations before function annotations existed in Python 3. So that means that I can have the same function Python 2 and 3, and just by turning that type annotation into a comment, it has the exact same behavior. This PEP also introduced some special type constructs. So these are fundamental things we needed to do static typing. So these are, it takes all the existing types and then allows us to construct new types as well. So these are types like any. Any would match at the type of anything at all. Union would be the combination of two types. Optional would be an alias for the union of none and some existing type. Tuple, uncallable, et cetera, would match those similar objects in Python. So then we could write something like this. We could have a frobnicate function that takes an integer, and then optionally it could take an int or a float, and then the return value, again, could be either an int or a float. So once we have these special type constructs, we have a more powerful type system here. It also defines some container types. So these are ways that we can define types inside of container classes like dictionaries and lists. And so that would look something like this, right? If I have a list of integers, I can define the type of that container class and the values that will be stored inside it. And the same for dictionaries. I can have a dictionary where the key is always a string and the value is always an integer. And also there are generic types for when we want something to just behave in a generic way. So in Python, we have things like an iterable. An iterable can be this whole class of objects that have the features of an iterator. So we also have types like iterable that we can use to represent and type things that we don't necessarily care if it's a list or if it's a dict. We just want to be able to iterate over it. It also defined the relationships between types, subtypes, and classes. So like I said before, a type is actually just a class. So for things like int, I can call type on it, and again, I just get the class. And that just gives me the current class that's in scope. So if I define a new class, I call type on it, I get that class as well. Int is both a type and a class that can be instantiated, but it's important to note that while I can define custom classes, and these are both types and classes, those special type constructs that I mentioned before, like union, those are types, but they're not classes. I can't instantiate a union. It doesn't really make sense here. And finally, we can also, with this theory of type hints, we can do type aliases using union. So this would allow us to do, if we wanted to be more like JavaScript, we could have a single number type that unifies all numbers in Python. All right, so that was the theory of type hints. And then we had PEP 484, which basically standardizes everything in PEP 483 and basically standardizes around what MyPI was currently doing. And it's basically, this PEP is how to build a type checker for Python. It introduces a typing module, introduces a lot of details about edge cases and specific use cases. And yeah, it basically leans really heavily on what MyPI was already doing. So we got that in PEP. In Python 3.5, we got that with PEP 484 support and with a typing module. And then we got PEP 526, and this allowed us to do inline variable annotations. So this was allowed us to do something like this, where before, for variables, we'd have to use these type comments, and now we can do it inline. So primes is like this. One problem with the comment annotation syntax was that it's hard to initialize a type for a variable that doesn't have a value yet. So with the inline variable annotations, we could do something like this, where we just say, that variable is a string, I don't care, it doesn't have a value yet. And same thing for class types. Like here, stats is a class variable. I could instantiate it correctly like this with inline annotations. So we got that in Python 3.6. And then we almost had everything to do static typing in Python. But then we need a type checker. And that was basically MyPI. It's the last piece of the puzzle. It's not included with core Python. It's a third-party tool. But the idea is that we have a couple different types of type checkers. We have either static or dynamic type checkers. And a dynamic type checker, a static type checker is going to type check your code at rest, right? It's going to look at your source. It's not actually going to evaluate any of it. It's going to do it totally statically. Whereas a dynamic type checker is going to be kind of like those asserts that we were doing before. It's going to happen at runtime. It's going to evaluate those types as your program executes. So MyPI is a static type checker for statically typed Python. And like I said, it's just a tool. You can pip install it. It's available on PiType. And if you run it, it kind of looks something like this. You can install it, create a file with some static types. And then if they're wrong, it will warn you. It will tell you, hey, you told me that this argument should be an integer. It looks like you're calling it with a string. That's a type error. So there are actually a bunch of type checkers besides MyPI. So like I said, there are static and dynamic ones. The static ones kind of align with all of the large Python shops that exist. So MyPI is mostly owned by Dropbox these days. Google has PiType. Facebook has Pyre. Microsoft has PyWrite. PyCharm actually has a type checker built into the IDE. And actually, you can use any of these type checkers with whatever your IDE or development environment is as well, right? Most of them integrate into some Python environment. Okay, so disclaimer, I work at Google. So one of the questions that I often get about type checking is, so what is the difference? Like, if these all implement PEP 484, what's the difference between them? And so I've actually only used MyPI and PiType, so I'll tell you what the difference is between those. The answer is not a whole lot. Basically, it comes down to a philosophy. So PiType is also available from PyPI, and you can install it. And the main difference is that, like I said, it's a philosophy. And basically, the philosophy is that PiType will only give you a type error if it will actually become a runtime exception. Whereas MyPI is going to be a lot more strict about actual usage of types. And I'll show you some examples. So here I have two functions. One returns a string, and the other takes the call to that function and adds it to an integer. So if I were to run this, it would be a type error, right? I'm trying to add a string to an integer, and that's a problem. If I run it with MyPI, MyPI actually passes. It says that this is fine. And the reason is because it is unable to do type inference across multiple functions. However, if you were to run this with PiType, it would actually say, yeah, if you ran this at runtime, you would get a type error, and that's a problem, and it would give you an error. And actually, the inverse is true as well. So PiType is going to be more lenient in situations where it's not going to produce a runtime error. So here's an example of a function. It takes a list. The list has a string inside of it, and I append an integer in it, iterate over it, and print it. So basically, this is going to succeed if I try to run this. It's totally valid, although it might be a little bit confusing to mix strings and integer here. So if I run this, it correctly has a list of strings. PiType says there's no errors here, but MyPI is going to complain, thanks, because you're trying to append an integer to a list of strings, and it's incompatible. All right, so those are the differences. You might now say, why? Like, this is all great. It's great that we have this in Python. Why do I want to use it? So first I'll say when you shouldn't use static typing. And the answer to that is basically never. It's not going to hurt you. It's not painful to use. One case when you might not want to use static typing is if you're going to use it to replace your unit tests. Static typing is not a replacement for unit tests. A lot of times unit tests end up being something that ends up looking like you're checking the types of your program. But it's not. And actually, you probably need both static typing and unit tests simultaneously. Yeah, there is kind of an argument about this, but yeah, you need both. So when should you use static typing? Basically, use it as much as possible. Use it liberally. Use it in these situations. So maybe when you're millions lines of scale, right? Like I said, that much dynamically typed Python is a liability. And so if you have millions of lines of Python code, you probably already know this, but you should maybe start statically typing it. Dropbox found that at their scale, it would start to produce really needlessly hard to understand code that impacted developer productivity. So that's why all these big shops like Google and Facebook have invested in static typing, because it actually makes their developers' lives easier. And yeah, static typing is a liability at that scale. or the lack of it. So you can imagine a graph that kind of looks like this, where as your lines of code go up, your desire to add type annotations goes up, and the ease of doing it goes down. So you are probably like here, unless you are Facebook, Dropbox, or Google. This is the good time to add static typing. That's probably actually when you're going to do it. But keep that in mind when you're evaluating when to start adding static typing. It's easier to do it earlier. You should use static typing when your code is confusing. So let's be honest, we've all written confusing code. You can sort of think of static typing as machine-verified documentation, right? So you add typing to your Python function that's extremely confusing, and it will tell your developer what that function should expect and return, and it will also allow you to verify that it's actually being called that way. So if you feel the need to document the input and output of a function, then that's probably a hint that you should just statically type it. You should use static typing also when your code is for public consumption. So let's say you're like publishing a module on PiType. Adding type annotations help the developers that use your module know how to use it. And also means that if they are using static typing in their code base, they will really appreciate the fact that you're publishing types for your code base as well. Another good time to use static typing is before doing a big migration or doing a big refactor, right? Go and add static types to everything that you're about to change, and then change it, and see if you get a bunch of type errors. Because if you do, it means you're calling some function wrong. You missed some part of your migration. And finally, you can also use static typing to just experiment with static typing, right? Like I said, it doesn't hurt. It's pretty easy to just add some static types as long as you're in the latest version of Python that supports it. You can also use static typing if you are cold. Gary Bernhardt says, static types are a warm blanket that I have missed so much. So I guess static types make you warmer as well. And I have to point out Gary's background on Twitter right now is this. Here lies Gary, stung by type errors. That's really funny. All right, to conclude, here's how you can use static typing in Python in 5 easy steps. So first, unoptionally, you can migrate to a newer version of Python. Like I said, type comments will allow you to type older Python 2 code. But really, we should probably all be migrating to Python 3.6 or above. We're about to get Python 3.8, so you should at least be on 3.6. Second, you could just install type checker locally. I don't care which one it is. Install one, install multiple, it doesn't matter. And integrate it into your IDE. This will allow you to get these type notifications about your code as soon as you start adding just one line of static typing. Put that in install the type checker and integrate it into your editor. And then you can start optionally typing your code base. You could start with the hardest function that you have in your code base, the one that's most impossible to understand, or you can start with the easiest one, like the most simplest function. That'd be the easiest one to type. Just pick a critical area and start there. And then what you can do once you have a little bit of static typing is you can run your same type checker with your linting. So I'm assuming you're doing linting. Everyone's probably just running black now. Just add type checking as well. Just run MyPI at the same time. And finally, you can convince all of your coworkers to join you in the glory of static typing. And if you need help convincing them, immediately after this talk, there's another talk called Convincing an Entire Engineering Org to Use and Like MyPI. So you could just stick around, stay in your seats, and Annie will show you how to do that. Thanks, everyone.